Did you know about the Hessian? You use this every day, but you may not exclusively recognize it. Are you ready for an exciting unraveling of the matrix Hessian? Come, let's start the video. Now, as we promised that you would appreciate the Hessian matrix in its entirety, we are now going to look at the Hessian matrix in parts. First, let's idealize the Hessian matrix to be a diagonal one, and then we'll look at the effect of the mixed derivatives that are going to populate the anti-principal diagonal. Now, this is the function we are going to look at from the Hessian matrix perspective. And if you plot this particular function, you can see that you get a convex bowl. And if you project any section of this particular convex bowl, it would be a perfect circle. That is, I'm talking about the level curve. Now, I want to investigate the elements of this particular Hessian matrix in the context of this convex bowl. And first of all, let me construct this Hessian matrix before I get into those explanations. How do you actually construct a Hessian matrix? The Hessian matrix, assuming that it is a pure diagonal matrix, that means it would have 0 populating the anti-principal diagonal. That means each mixed derivative is equal to 0, and that is simply attributed to the fact that it is z is equal to x square plus y square, because when I seek the first derivative of z with respect to x, I am going to get 2x. The y square gets knocked out because that is a constant when you are differentiating with respect to x, and when you seek further derivative with respect to y, because I seek the mixed derivative, that is with respect to y, if you are partially differentiating this, then what you would get a 0, because this is pure function of x. If you're trying to differentiate that with respect to y, you're going to get a 0. So going by the nature of this equation, which is used to construct this convex bowl, you have the mixed derivatives 0. And if I differentiate this for the second time, what would be my second derivative? My second derivative obviously would be of z with respect to x would be 2, and by the symmetry of the function, the second derivative of y with respect to z with respect to y is also going to be 2. So that means this is my Hessian matrix. This is constructed by taking second derivative of z with respect to x, second derivative of z with respect to y, and then here you have the mixed derivative. Since there is no term which has both x and y, or both the terms are either x or y, therefore you cannot have a mixed derivative. Now let's start interpreting this particular matrix. What exactly it means when I have 2 and 2 populating the principal diagonal elements of the Hessian matrix. That means the curvature in x direction and the curvature in y direction both are equal, and both are equal to 2. And very importantly, we have just inverted the convex bowl, and at the global minimum, at the point where you have the global minimum, which is at the origin, because the minimum for this convex bowl function is of course 0, 0, 0. It coincides with this point. That means your z is 0, the value of the function is 0, and it occurs when x equal to 0, y equal to 0. At the minimum point, if I seek the curvatures at that point, you can see that I have marked out both the curvatures, both are equal to 2. And you can also see very importantly that the direction of the curvature is always given by a tangent drawn at that particular point. But if you see that I haven't drawn any tangents, that is because my tangent line would have coincided with the principal axis. That is, x-axis and the y-axis would have coincided with the tangents even if I were to draw over there. So that means when this matrix is absolutely diagonal, that means it doesn't have any off diagonal terms or anti-principal diagonal terms, then what exactly it means that the direction of the curvatures, which are given by the tangents at that point, exactly coincide with the axis, principal axis, because one is of course x, another is y. From both the directions, if you see, that is the curvatures are equal and their directions coincide with that of the axis. And why I am talking about the global minimum, and also you can see that we said when we were discussing the single variable situation, the maxima minima always occur at a point where the slope is 0, that is the tangent line is parallel to the x-axis. If I translate that in this situation, the tangent plane must be absolutely parallel to the xy plane, because you are talking about z is equal to x square plus y square. And you can very well see here, if you pass a plane tangentially through the origin, then that not only locates the global minimum, but also the plane is coincident with the xy plane. But if the plane were to be shifted up or down depending on where the complex minimum of the convex bowl function is located, then the equation would have been either z is equal to 0, which is the current equation. It could have been plus or minus d by whatever amount the plane would have got displaced. But nonetheless, the plane continues to be parallel to the xy plane, or it is coincident in this case with the xy plane. Very, very similar to a situation in single variable case where the tangent is parallel to x. Here the plane is parallel to xy plane. So this is what you got to observe. And since going by the nature of the convex bowl that we have developed here, since there are no xy terms, there are either x or y terms, pure x and y terms, the cross derivatives or the mixed derivatives do not come into picture. That is the mixed derivatives which are equal for the function if it is continuous. But here mixed derivatives are, both of them are 0. You can see very well here. And the Hessian matrix is populated only along the principal diagonal. That means the curvature directions coincide with x and y axis, because you seek curvature in each direction. There are two independent variables, x and y, and each direction you seek the curvature, and the curvature direction, mind you, is always given by a tangent drawn at the point where you are seeking the minimum or maximum. Here we are seeking the global minimum, and if I draw a tangent, that would actually coincide with the x-axis, and if I draw a tangent in this direction, that would coincide with the y-axis. So therefore the direction of principal curvatures are the elements of the Hessian matrix, because these are 0, 0. When the mixed derivatives are 0, these two themselves are the principal curvatures. If these were to be populated, then you cannot call these elements as principal curvatures, mind you. Then we will have to go for what are going to be called as the eigenvalues. We'll discuss later. But now, since these two elements are 0, these themselves are the principal curvatures. And in this case, you can see that both the curvatures are absolutely equal. And one of the things that you would see is that the level curve of this particular convex bowl is a perfect circle. It is not an ellipse. So therefore the curvature in each direction is equal, and also they coincide with the direction of the independent variable axis. How many independent variables are there? 2, x and y, and these principal curvatures which are equal and their directions coincide with the 2 independent variable axis. The take home is very, very clear. So this is the Hessian matrix, and if the mixed derivatives are 0, only the principal diagonal is populated, and this principal diagonal elements themselves are the principal curvatures. They are equal in this case, and if the mixed derivatives are 0, then one of the advantages is that the direction reckoning is very simple, because their directions coincide with the direction of independent variable axis. That's important. And secondly, you also observe that the plane which actually passes through the origin, which is the global minimum for this convex bowl, is coincident with the xy plane. Otherwise it would have been parallel to the xy plane, and that shows us why we incept with the gradient. When gradient is 0 for this particular function, z is equal to a function of x and y, the plane would be parallel to xy plane, which translates to a single variable situation where the tangent is parallel to the x-axis. So now next up, what we are going to look at is if the mixed derivatives are not going to be zero, if the Hessian matrix is going to be populated, then what is the role of these mixed derivatives? Okay, that's going to be interesting. So let's see what happens if we introduce non-zero mixed derivatives. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.